Welcome back to the course of chemical crystallography. In the previous lecture, we discussed about the origin of reciprocal lattice, how to construct a reciprocal lattice from a direct lattice, and we learned that every reciprocal lattice point in reciprocal space represents a particular plane in the direct lattice. So, by doing this, what we have done is we have constructed a reciprocal lattice from the planes that are having corresponding Miller indices HKL in the direct lattice. And then towards the end, we learned how to construct the reciprocal lattice in case of orthorhombic system and how to get the corresponding reciprocal lattice parameters A star, B star, C star and the volume. So now we will try to construct the same in case of monoclinic lattice. As you know, for monoclinic lattice, the angle between the A and C is not 90 and this is called beta. So I am drawing the AC plane of a monoclinic unit cell. So this angle is beta. So now if we drop a perpendicular from the origin to the plane which is parallel to C, this plane, this perpendicular will correspond to D100. In the same manner, if we construct the perpendicular from origin O to the AC plane here, to the plane parallel to the A axis is like the distance is D001, and then the angle between the two normals is my beta star. So now if the angle on that other side is beta, then the angle here is 180 degree minus beta, which is same as this angle 180 degree minus beta, and this angle is also 180 minus beta. So now OA, where I construct that as A and that as C, OA is equal to A and OC is equal to C. Then if we want to write down the value of D100 in terms of A and beta, this D100, so we consider this particular triangle and then we can write D100 equal to A sine 180 minus beta, which means it is equal to A sine beta. Similarly, D001 is equal to C sine 180 minus beta. We are talking about a triangle here, which is again equal to C sine beta. Now, D001 is perpendicular to 001 plane, and D100 is perpendicular to 100 plane. So the reciprocal lattice distance A star is nothing but equal to 1 by D100 and C star is equal to 1 by D001. So now A star is equal to 1 by D100 and D100 is A sin beta. So A star is equal to A sin beta and correspondingly C star equal to C sin beta. And obviously, since the direction B is perpendicular to both C and A, B star is same as 1 by B as was seen in orthorhombic system. So the angle beta star is equal to, let us see that. This is 180 minus beta. This angle is then beta. In case of this figure, you have this angle and that as 90 degree. So in case of this quadrangle, two angles are 90 degree. So this is 180 plus beta. So this angle is nothing but equal to 180 minus beta, because these two angles should correspond to 180 degree because the other two angles correspond to 180 degree. So beta star is equal to 180 degree minus beta. So if we try to calculate the volume of a monoclinic system, which is equal to ABC sin beta, the reciprocal lattice volume is nothing but V star is equal to 1 by V, which is equal to 1 by ABC sin beta, or equal to A star, B star, C star sin beta star. So this is how one can calculate the reciprocal lattice parameters for monoclinic system. In case of triclinic, this representation becomes even more complicated because the angles alpha, beta, gamma are all non-90, and hence the relationships are more complicated, as I have shown here in this presentation, which is also taken from a textbook. Now let us see how we can visualize Bragg's law in reciprocal lattice. Here in the figure on your left, I have taken the section of A star C star plane of reciprocal lattice. So the grid lines that are visible here, it corresponds to the reciprocal lattice points. So every point of intersection of these lines represent a reciprocal lattice point in the A star C star plane, and we assume that this O as the reciprocal lattice origin, and the direction XO is the direction of the X-ray beam that is falling on this particular crystal. So now what we are trying to do is to draw a circle in such a way that O falls at its circumference, C is the center of the circle, and OC is equal to Cx equal to 1 by lambda. That means we are trying to construct a circle with radius equal to 1 by lambda. Lambda is the wavelength of X-ray radiation. So, this circle is formed in the plane of the A star C star reciprocal lattice plane, and O falls at the circumference of the circle. After drawing this circle, we find that another reciprocal lattice point P, which is here, is falling on the circumference of this particular circle of radius 1 by lambda. So then we consider a triangle OPB, which is here, OPB, which is a right angle triangle, and then we try to calculate sine OBP, sine of OBP, where the angle OBP is equal to theta, because when we are trying to see, now let us concentrate on the figure on the right hand side. The incident X-ray beam is making an angle theta with this particular reciprocal lattice plane, which means this angle is theta. As a result, the angle OBP is also theta. So OB and sine OBP is equal to OP by OB, OP by OB, and now OB is nothing but the diameter of the circle, which is equal to 2 by lambda. So we can rewrite as sine theta equal to OP by 2 into lambda. Now, as P is another reciprocal lattice point, then the distance OP must correspond to 1 by DHKL for the reciprocal lattice point P, because this OP is perpendicular to OB. So we are dropping a perpendicular from the origin and coming to a point and cutting it at P, which is a reciprocal lattice point. So the corresponding distance OP is supposed to be 1 by THKL. That is the underlying principle of generating the reciprocal lattice points. So we replace OP equal to 1 by DHKL, and we write sine theta equal to lambda by 2 DHKL, or we can write lambda equal to 2 DHKL sine theta. That means the Bragg's law condition is satisfied for this particular reciprocal lattice point P. So, what are the implications of this understanding? Whenever a reciprocal lattice point coincides with the circumference of the circle drawn like this, with the lambda, with the radius 1 by lambda, Bragg's law is satisfied and the diffraction occurs. The reflecting plane is perpendicular to OP, hence parallel to BP. So the plane which is the reflecting plane is perpendicular to OP. Reflecting plane is perpendicular to OP, which means parallel to BP, where BP is perpendicular to OP. The direction of diffracted beam is OD. Is parallel to the direction CP. That means it makes an angle 2 theta with the incident beam as shown here. That means when we try to observe a diffraction coming out of a set of parallel planes, we measure it at an angle 2 theta with respect to the incident beam. So now this particular drawing which we have seen here is only in one particular reciprocal lattice plane of A star C star. Like that, you have sets of planes in A star B star direction or C star B star planes. As a matter of fact, these reciprocal lattice points are there in all directions in 3 dimensions, and if we consider those points, it actually represents a sphere. So when you represent a sphere like that, immediately the size of the sphere is related to 1 by lambda. That means smaller the value of lambda, larger the value of 1 by lambda, larger the value of lambda, smaller the value of 1 by lambda. So for radiations with smaller wavelength, we should have a larger sphere as shown here in case of MOK alpha radiation, and in case of longer wavelength like copper K alpha radiation, where the wavelength is nearly double that of molybdenum, the sphere that is constructed is of smaller volume or smaller diameter. And when we have understood the formation of reciprocal lattice from a direct lattice, this equation at the bottom is another representation of Bragg's law in reciprocal space. So this expression is one of the most important expressions in the theory of X-ray diffraction, a representation of Bragg's law in terms of reciprocal lattice constants. So now if we consider the sphere with radius 1 by lambda as shown here, we get a smaller sphere with radius 1 by lambda, and then with radius of 2 by lambda, which is the diameter of the smaller sphere, if we construct another sphere having the center at the point of intersection here, a sphere with radius 2 by lambda is called a larger sphere, and this larger sphere is called the limiting sphere, and the smaller sphere with radius 1 by lambda is called the sphere of reflection. So this sphere of reflection is also called the Ewald sphere after the name of Paul Peter Ewald, a German physicist and crystallographer, and he introduced this concept of sphere of reflection and limiting sphere in his article in 1969 in Acta Crystallographica. The reference is given here. What are we trying to understand from here? In the next slide, I will show you a presentation where we will see that all the reciprocal lattice points which are falling within this limiting sphere of reflection can be made to pass through the sphere of reflection. So from limiting sphere, the reciprocal lattice points which come within this limiting sphere, by rotating the crystal in front of the X-ray beam, one can make those reciprocal lattice points to pass through the Ewald sphere, and once a point is passing through the circumference of this Ewald sphere, the periphery of Ewald sphere, it makes a diffraction to happen. So utilizing this concept and thinking that, assuming that there is one reciprocal lattice per unit space, per unit reciprocal lattice volume, one can calculate the number of reflections that can be originated from a given crystal. So the number of reflections that can happen, that can be obtained from a given crystal, can be calculated as 4/3 pi 2 by lambda cube. 2 by lambda is the diameter of this particular limiting sphere. So whatever reflections fall within this limiting sphere of this volume can be recorded, and one can get the data for those reciprocal lattice points. So then the value of n can be calculated in terms of direct volume of the direct lattice, or that is volume of direct unit cell, in terms of if we know the wavelength of diffraction. So just for one example, when we have an orthorhombic unit cell of volume about 1600 cubic angstroms, if we use copper K alpha radiation, which has wavelength of 1.54 angstrom, one can get about 14,600 reflections, whereas if somebody is using molybdenum K alpha radiation, this number of reflections suddenly jumps to 1,49,000 reflections using molybdenum. That means by using a smaller wavelength, one can achieve a larger number of reciprocal lattice points. That means one can achieve a much higher resolution. So in this particular presentation, I will take help of this animation, which is available in the website of Professor Branton Campbell, and let us try to show here. This point is the source of X-ray, as we can see, and then we choose a crystal oriented in a particular direction, and we choose a radiation of molybdenum. So in this presentation, what is visible is that these bright red spots are reciprocal lattice points, and the crystal in the center is rotated in such a way that these reciprocal lattice points are rotating in front of the beam, and as and when a reciprocal lattice point is crossing the Ewald sphere, it is making diffraction. So now if we change the radiation from molybdenum to copper, you see that the size of the sphere has become much smaller. So the number of reciprocal lattice points falling within the limiting sphere of diameter 2 by lambda has reduced. So the number of reflections that one can achieve has drastically reduced. If I choose a different lattice, different crystal, here what you can see, it is a zinc blende crystal in a particular plane, and in the reciprocal lattice what you can see is some bright red spots and some red spots which are not bright, which are sort of disappeared. And when those bright spots are crossing the Ewald sphere, it is making a diffraction, and when those dull spots are crossing the Ewald sphere, it is not making any diffraction. This indicates that not all reciprocal lattice points while crossing the Ewald sphere will make a diffraction to happen. So what is happening? This is a phenomena called systematic absence, which we will learn in the next slide. There are cases where a set of reflections will be systematically absent and will not be observed for various symmetry constraints, and only some of those reflections which are bright in this presentation will be visible. Again, if we change the radiation to copper, you can see that the total number of accessible reflections has reduced drastically. So now, in order to understand the origin of this systematic absence, I once again would take help from a two-dimensional presentation. Suppose this is a two-dimensional primitive lattice where you have lattice points only at the corners as shown here. So now if we draw a set of planes 1, 1, which is passing through the corners like that, these planes will always have their corresponding incident beam and coming out diffracted beam, and at some particular angle of theta, the diffraction angle, it will give you X-ray diffraction from 1, 1 set of planes. Similarly, if we construct the set of 2, 1 planes, which means it connects from one unit cell, the corner of the other unit cell passing through the midpoint of the other direction. So this 2, 1 set of planes having a distance d to 1 will also meet the condition for Bragg's reflection. But now if we consider a centered lattice in 2 dimensions where we have atoms at 4 corners and an atom at the center of the lattice, in that case, when we try to construct the 1, 1 set of planes where this distance is d1, 1, there is no problem. A diffraction would occur at a suitable direction where the Bragg condition is met. But in this case of 2, 1 set of reflections, suppose the dark lines are parallel and these dark lines, the interplanar distance is d2, 1. Once again, the lines which are dashed lines, the distance between them is also d2, 1. You see, both the dark and the dashed lines represent the same set of planes 2, 1. That means the planes with dash and the bold line have the similar indices. So that means this distance is half of d2, 1. What will happen? The planes at a distance d2, 1 meets the Bragg condition of integral multiple of wavelength is equal to the path difference, then obviously this will not meet the diffraction condition. As a result, the constructive interference will not happen, and in this particular case only the destructive interference will happen, and we will not see any diffraction from the set of 2, 1 planes. So from a diffraction pattern of a centered lattice like this in a 2 dimension, the 2, 1 set of planes will be systematically absent. For the time being, I am only introducing you to this lattice centering and the corresponding systematic absence conditions, but at a later stage we will be able to derive these conditions using some equations. So in case of a centered lattice, that means the BC face is centered, B and C means K and L. So for general reflections HKL, K plus L when it is odd, 2n plus 1 means it is odd, the reflections will be absent. That means in case of A-centered lattice with any value of H, when K plus L is odd, say for example 2, 1, H 1, 2, H 3, 2 and so on, these reflections will be absent systematically in case of A-centered lattice. Similarly, for B-centered lattice, H plus L will be odd. For C-centered lattice, H plus K will be odd. Now, in case of face-centered lattice, when all the three conditions need to be simultaneously fulfilled, that means for face-centered lattice, in all the cases H plus K should be odd, H plus L is odd, K plus L is odd. That means H, K and L not all even or all odd. So, in this case, only reflections which are like 2, 0, 0, 2, 2, 2, 2, 4, 2, this type of reflections will be present and any other reflections will be absent. Similarly, all even, all odd also will be present. So 1, 1, 1, 3, 1, 1, these are all odd set of reflections and they will be systematically present, all others will be systematically absent. Similarly, for body-centered lattice, this condition has to be fulfilled, that is H plus K plus L is odd, will be systematically absent. So, the absent reflections will be of this type: 1 plus 1 plus 1, 3, 2, 1, 2 and so on, where the sum is 3. So, in the next lecture we will try to understand how the systematic absence conditions for glides and screw axis to be followed.